section 2.1 on power and radical functions. So example 1 says to graph and analyze the function 1/2 x to the 6th power. We're going to talk about the domain and range, the x and y intercepts, end behavior, continuity, and when the function is increasing, decreasing, and or constant. So first off, I'm going to look at the graph of this function, and then we're going to find all of those things algebraically. So this is the graph of 1/2 x to the 6th power. It's going to look very similar to a quadratic function, which is to the 2nd power. Anything that has the same exponent, if it's an even exponent, 2, 4, 6, is going to look like a parabola. If it is an odd exponent, then it's going to look like the cubic function, very similar to those. Now, if I zoomed in at the origin of this graph, it's not flat down there at the bottom. It gets very, very close to flat, but it's never going to be constant down there at the bottom. So you could zoom into that and look at it. I've got another view here with the table, and you can see that the values are increasing drastically on the left and right hand side. They're both going up. Okay, so let's talk about the domain of this graph. You can see from the picture that the graph is going up on the left and right hand side. So as the graph is going up, it's going to continue going to the left and continue going to the right. So we would say then that the domain is from negative infinity to positive infinity. And the range, it does keep going up forever, but the lowest y value is actually 0. So for the range, we would say that it goes from 0 to infinity. And notice I use the bracket around a 0 because it actually does equal 0. Next thing we're going to look at is the x and y intercepts. So for the x-intercept, this is where you're going to plug in 0 for y and solve. So if I say 0 equals 1/2 x to the 6th power, I want to solve for x. So first step I'm going to do is multiply by 2 on both sides. Well, that will leave me with 0 equals x to the 6th power, and then I could take the 6th root of both sides, and x is still going to equal 0. So my x-intercept is 0, 0. To find the y-intercept, you're going to plug in 0 for x. So y equals 1/2 times 0 to the 6th power, and this is going to equal 0 as well. So if the point is 0, 0, that point is going to be an x-intercept and a y-intercept. Next, we want to talk about the end behavior of this graph. You always look at the highest exponent and the coefficient of that exponent. Since this highest exponent is an even number and the coefficient is positive, then that tells me that the end behavior is that it's rising on the left and right. And you can see that from the graph as well. This is a continuous function. There aren't any asymptotes on the graph. There aren't any breaks in the graph or holes, so it is a continuous function. Next thing we're going to look at is when the function is increasing, decreasing, and constant. And remember, we look from left to right. So from the left of the graph to the right, you can see that it's going down for a time, and then it flips and it starts going up. So the decreasing section of this graph is from negative infinity to 0, and then it starts increasing from 0 to infinity. There are no constant parts on this graph. Even though it kind of looks flat in the middle, you could keep zooming in and it would not be flat in the middle. Okay, example 2, same thing. We have the function 1/2 times the 5th root of 3x minus 4. And we're going to do the same thing. We're going to look at the graph and talk about all these parts of the graph. So here's the graph of this function. One way that you can actually type this into your calculator is if you type 1/2 times 3x minus 4 raised to the 1/5 power. It's the same function as this one. And some calculators, if you try typing it in with the 5th root, it may not come out correctly. So raising to the 1/5 power also works. Okay, so this is the graph of our function. And here's the table. You can see lots of decimal values in here because you would wind up taking the fifth root of some number, so that would give you a decimal. So first, domain and range. You can see that this graph is going to continue going to the left and to the right forever. So that's from negative infinity to positive infinity. And as it continues left and right, it's also going to continue up and down. So the range is also negative infinity to positive infinity. Okay, next thing for our intercepts, I'm going to start with the y-intercept this time. So I'm going to plug in 0 for x. So I have y equals 1/2 times 3 times 0 minus 4 raised to the 1/5 power. And you can type all that in at one time if you want to, or you can use order of operations to simplify. When you simplify, you should get that y is approximately negative 0.6598. So my y-intercept is at 0, negative 0.6598. For the x-intercept, we're going to plug in 0 for y. So 0 equals 1/2 times 3x minus 4 raised to the 1/5 power, or you could have left it as the fifth root. So I multiply by 2 on both sides. 2 times 0 is 0. To undo the 1/5 power, or to undo a fifth root, we're going to raise both sides to the fifth power. So 0 to the fifth power equals 3x minus 4. So that's going to be 0 equals 3x minus 4. When I solve for x then, x is going to equal 4/3. So my x-intercept is at 4/3, 0. Okay, the end behavior of this function, since it is to the 1/5 power, that is odd, so the ends are doing opposite things, and the coefficient is positive, so overall the graph is positive. So this is falling on the left and rising on the right. This is also a continuous function. There are no breaks, jumps, or holes in the graph. And then this function would be always increasing from left to right. There isn't any change in the behavior from left to right. It's always increasing from negative infinity to positive infinity. Okay, so now we're going to look at how to solve a radical equation. So I have in example 3, 12 equals the cubed root of x minus 2 squared plus 8. So when you're solving radical equations or power equations, the goal is to get x by itself, so you have to undo those radicals or undo those powers. So first thing I want to do is get rid of the 8 that's being added at the end. So I'm going to subtract 8 on both sides. So 12 minus 8 is going to be 4 equals, and I went ahead and wrote this as x minus 2 to the 2/3 power. The cubed root is the same as the 1/3 power, so 1/3 times the 2 power that was already there is 2/3. And there's several different ways you can solve this problem from here. You can do it in 2 steps or 1 step. I'm going to do it in 2 steps. So what I'm going to do is get rid of the 1/3 power by raising to the 3rd power on both sides. So 4 to the 3rd is going to equal x minus 2 squared. 4 to the 3rd is 64. So now to undo the square power, I'm going to take the square root of both sides. And remember, when you take the square root of a number, it's going to be the positive and negative square root. So this is the positive and negative square root of 64 is plus or minus 8. Equals x minus 2. So then I'm going to add 2 to both sides. I'm going to have to do it 2 times for the positive and the negative 8. So I'm going to get that x equals 10 or x equals negative 6. You always want to plug these back into the function to make sure they will actually work. So I'm going to fast forward here and show you the work for both of these. So when I'm checking my answer, I don't put an equal sign until I know for sure that it is equal to. So I plug in, I simplify as much as I can. I'm actually showing you kind of 2 different methods on this problem. It doesn't matter if you do the cubed root or square. In either order, you can work that out. So as long as it works, then those are solutions. And for both of these, 10 and negative 6, they equaled 12 when I plugged it into the equation. So both of these are solutions to this equation. You always want to check your work. You don't have to show all of the steps, but make sure that you do plug in, because there are going to be times where you get an answer that actually when you plug it back in is not a solution. Okay, so now in example 4, we have the square root of x plus 1 equals 1 plus the square root of 2x minus 12. Anytime you have several or multiple roots or radicals in an equation, it's going to take several steps to finally get rid of all of them. So the first step I want to do is I'm going to square both sides of this equation. That's definitely going to help me with the radical that's on the left-hand side. It's going to create a little bit of a mess on the right-hand side. So when I square the square root of x plus 1, that's just going to be x plus 1. On the right-hand side, I'm actually going to have to FOIL this binomial out. So I'm going to write it 2 times, 1 plus the square root of 2x minus 12 times itself. And I'll need to FOIL these 2 out. So when I FOIL this, 1 times 1 is 1. That's the first term. The outside and the inside terms are going to be the same, so it's actually going to be 2 of whatever you get. So 1 times the square root of 2x minus 12 is the square root of 2x minus 12. And then there would be 2 of them, so I put a 2 in front. Last, when I multiply the square root of 2x minus 12 times itself, the square root's going to cancel, and I'll just be left with 2x minus 12. So we're going to collect like terms. So I'm going to have x plus 1 equals 2x squared, or 2 times the square root of 2x minus 12 plus 2x minus 11. Now I'm going to move anything without the radical to the left-hand side. So I'm going to move the 2x and the negative 11 over. So that's going to leave me with negative x plus 12 equals 2 times the square root of 2x minus 12. We could divide by 2 at this point, but it's going to give me a fraction on the left, and I want to work with fractions as much as possible, without fractions anyway. So again, we're kind of at the same predicament as the beginning. I still have a radical in my equation, so I need to square both sides to get rid of that radical. On the left-hand side, we're going to multiply negative x plus 12 times negative x plus 12. So when I multiply or FOIL that out, I'm going to get x squared minus 24x plus 144. On the right-hand side, I'm going to have to square the 2, so that's going to give me 4. And then the radical is going to cancel out with the square. So 4 times 2x minus 12. So now I'm going to distribute that 4. So that will give me 8x minus 48 on the right. I'm going to go to a new slide, and I'm going to keep that same equation so that we can move on from here. I've cleared out all of my radicals. Now I notice this is a quadratic equation, so I need to move everything to one side and set it equal to 0 in order to solve. So I'm going to subtract 8x and add 48. So that's going to give me x squared minus 32x plus 192 equals 0. Now remember from Algebra 2, anytime you have a quadratic function, you can use the quadratic formula, but it's easier if you have the problem is factorable to factor it instead. So I'm going to factor this one. So I know the two things that multiply to get x squared are x and x. And then I need two numbers that multiply to equal 192, and they have to add or subtract to equal negative 32. So I kind of did some work out to the side and found all of the factors of 192 and came up with possible combinations that would add or subtract to equal negative 32. And I found that negative 8 times negative 24 equals 192. And negative 8 plus negative 24 equals negative 32. So those are my factors. So since I have x minus 8 times x minus 24 equals 0, that means those two factors equal 0, and my solutions would then be positive 8 or positive 24. So again, like example 3, you always want to plug back in and make sure that those solutions are valid. So I'm going to show you the work for both of these. So here's the work for plugging in 8, and I did get that 8 was a solution. When I plugged in 24, I got a false statement at the end. I got a statement that would say that 5 is equal to 1 plus 6, and 5 is not equal to 1 plus 6. So the number that we plugged into that, 24, is not a solution. So for this problem, x equals 8 is the only solution. So always check your work, double check, plug back into the equation to make sure it's valid.